So what's the big deal about the network layer? What's the big deal? What do we have to talk about at network layer? Number one, the first thing I need you to understand at this network layer is what we call your message at network layer. We call the message packets at network layer. Packets. You remember when I first introduced you guys to the OSI model, I said when the journey will start from application layer, then to presentation layer, then to session layer, then to transport layer, then to network layer. So at network layer, our data is called packets. Why did they change the name of the data? Is it that the data is lost on transit or what? No. I have said this again and again. When new messages or new information are added to that data so that it can help the data to get to destination, they give it a new name. So if I'm talking now and I say, oh, one packet got lost, two packets got lost, because these are our terminologies in this feed. These are our terminologies. So when I say packets, you should know what I'm talking about. That doesn't mean that I'm not referring to the whole data as a whole, but I'm basically talking at layer 3. So network layer is layer 3. Don't forget that from our OSI model. You are starting from down. Physical layer is layer 1. Data link layer is layer 2. Network layer is layer 3. So at that layer 3, we call our message packets. We call our message packet. So what is the big deal? What happens at this network layer? Do you know the most important thing here? Source IP address and destination IP address. This is where it is added to our message. Not MAC address, guys. Source IP address and destination IP address. This is where it is added to the message. So if I am sending message, this is Roland, sending message to the class rep, I have my layer 2 address, which is my MAC address. I have my layer 3 address, which is my IP address. Both of these addresses must be completed in the message before the message can move. Before the message goes to the destination, I will put my own source MAC address and the destination MAC address, the person I'm trying to talk to. I will put my own source IP address and the IP address of the person I'm trying to talk to. So at layer 3, that is where the source IP address and destination IP address are added. And that is why one of the most important protocols at layer 3 is IP. Take note, the most important protocol, one of the most important protocols, in fact, the most important protocol at layer 3, I make bold to say that now. The most important protocol at layer 3 is IP. What is IP? Internet protocol. That is the most important protocol at layer 3. And of course, now we have IP version 4, we have IP version 6, and we're going to go into all of that. We have a class dedicated to IPv4. We have a class dedicated to IPv6. These are separate classes, separate topics. We're going to come there. But we're just learning in general about the OSI model and the protocols that operate at each of these layers. And you can see them here again. You can see them here. Look at our layers. Layer 1, physical layer. Layer 2, data link layer. Layer 3, network layer. And the most important protocols at that layer are, the most important protocol is our IP, either version 4 or version 6. They operate at this network layer. I remember telling you or showing you guys in this class, when you go to your computer, how you can see the MAC address and the IP address of your computer. When you go to command prompt and you say ipconfig/all, you will see I am using a wireless card. Look at my IP address here. IP version 4 address. That's my layer 3 address. That's my IP address. Look at my MAC address here. That's my physical address. That is my layer 2 address. So both addresses must be completed on the message that is going to travel from source to destination. There's one more thing that needs to be completed before it can travel. We are going to come to that when we come to transport layer. So this IP we are talking about, internet protocol, internet protocol, internet protocol. It's all about IP addressing. And that happens at layer 3. It takes place at layer 3. Don't ever forget that. So let's move on. So they said the network layer provides services to allow end-to-end devices to exchange data. All of them do that. Just that this one is just who is this? Sorry guys, let me remove my WhatsApp. Sorry guys, so sorry about that. Okay, so let me continue. So they said network layer provides services to allow end devices to exchange data. It's not only a network layer that will do that. It's not only network layer. It's not only network layer. All of them will do that. But we are just particular about what is happening at network layer. And I've already summarized that for you guys. So these are the two protocols that operate at that layer. Now look at what they wrote here. The network layer performs 4 basic functions. Addressing end devices. That is the most important thing. IP addressing. That is the most important thing, guys. Now the question will not be, so this IP addressing I'm talking about, who will give the address to the computer? It depends. You can get to the computer and you can send the computer to go and get it from somewhere, which we call a DHCP server. We're also going to get there. You need to understand how this thing works, how they connect together. Addressing end-to-end devices. Addressing end-to-end devices. So you need to understand this thing. That's the most important thing. This encapsulation you are looking at now is not, layer 3 is not the only one doing it. The encapsulation we're talking about here, layer 3 is not the only one doing it. But when you come to routing, guys, this routing here, I'm not saying layer 3 doesn't do encapsulation, it does. And it does the encapsulation. What is encapsulation and the encapsulation? I have told you when the message is coming from application layer, it's coming as data, data, data. By the time it gets to transport layer, we call it segment. What is the big deal about the segment? It's just like you remove the letter, you put it in an envelope, and you label it. Source port number, destination port number. That's what happens at transport layer. Source port number, destination port number. We're going to come there. That's the most important thing there. But guess what? When the message gets to data link layer, network layer, this network layer too, we carry that envelope, throw it in another envelope, seal it, and put source IP address, destination IP address. That is what they are referring to as encapsulation. When you get to data link layer too, we carry that envelope, drop in another bigger envelope, and now put source MAC address and destination MAC address. So it's like you do your own part, put it in an envelope. When the envelope gets to me, I'll carry my own envelope, drop your own envelope in my own envelope, put the source IP address, destination IP address, and then allow you to move to the next level, depending on where it's coming from. And don't forget, I have told you, from the source, it goes through the process of encapsulation. But when it gets to destination, it goes through the process of de-encapsulation. De-encapsulation. So all of them do encapsulation, all of them do the encapsulation. But I'm talking about something that is specific, that is different. And that is addressing end devices. And of course, routing, guys. Routing. This is a world of its own. We are going to spend like 4 weeks on routing. Maybe 3 weeks or 4. I think 3 weeks. It's a world of its own. And this happens at layer 3. So for people that will be looking at what is this routing all about, we're going to come there. Because that is another thing that if you know it and you know it well, it's very easy for you to branch in some areas in cloud computing because you understand routing. You understand switching. That's just by the way. So network layer, source IP address, destination IP address are added to the message. And of course, routing takes place. And the most important protocol at that layer is referred to as IP. Look at what is going on here now. Something coming from layer 4, we have a segment header. Segment header is at layer 4, transport layer. By the time it comes to network layer, that particular is like that envelope I spoke about. You carry that one and throw in another envelope. Do you now label your own? We now have IP header. So what is in this IP header? Source IP address and destination IP address. Source IP address and destination IP address. I remember class rep asked a question one time like that. Maybe I answered it or not. I can't remember. But let me just brand it. I just remember. When you talk about PDU, protocol data unit, protocol data unit, what's the big deal about that? They're simply asking you, what does your data become at each of these layers? Or what do you call the data at each of these layers? Or at different layers? What do you call data? I've told you application layer is data. Presentation layer is data. Session layer is data. By the time the data gets to transport layer, we call it segments. That's a PDU. Protocol data unit, meaning it's like the encapsulation, the new format or something, or let me say the new name. Then when the data gets to network layer, we call the data packets. And when the data gets to data link layer, we call the data frame. And when that data gets to physical layer, we call the data bit, because that is where it's converted to zeros and ones, guys. All of this is what they refer to as PDU, protocol data units. What you call data at each of these layers. And I like to refer to the one that has changed, because from application, presentation, and session, they did not really change from the OSI model. And why didn't they change? Don't forget, 3 of these layers were bundled together to give us one layer in our TCP/IP model, which is the real model that is in use today, application layer. So when you are talking about application layer, it's only one layer, that is application layer in TCP/IP, and that is one we're using today. That's why data is just data, and then they move to segments. But because OSI model is detailed, it's more detailed. If you can see that I'm okay now, my energy is, I'm pumping, the anointing is moving. Don't mind me, oh. So you can see that the data is the OG is running, it's okay, the guy is feeling fine now. So you see that 3 layers were bundled together, 3 layers of the OSI model were bundled together into one layer of the TCP/IP, and that is the real model we are using nowadays. So when you now talk about TCP/IP model, when you say data, data is data only at application layer, then you move to transport layer, and then you now talk about segment. Then you move to internet layer, you know, they change the name. Then you talk about packet. Then the reason why we now go back again to OSI model is because we have 2 layers to talk about 2 different things, which is our frame and bit. We don't want to bundle them together. I listened to one guy's video. He said the only reason why we should talk about the OSI model is because the people that came out with TCP/IP model, if they had given or let me say gone to TCP/IP model with this data link layer and physical layer separate, we'll never talk about OSI again. Because we need to point to you that something happens at data link layer. We need to point to you that something happens at physical layer. We don't want to bundle them together like they did in TCP/IP, and that is the reason why we still use OSI model to teach in our class, because it's detailed. It's much more detailed. Now, like a class, I taught a class in the university today. I told them, I said, that's just introduction to reference. I said, your takeaway from this class, you should know the layers between these, the number of layers in OSI model, TCP/IP model, the similarities and their differences. And you should know that TCP/IP model is a modification of OSI model. Take note of that, guys. So this is where your IP address is added, source and destination. I've said that. But there are some concepts you need to understand here. The IP address does not change from source to destination. This is interesting. You need to know that. Unlike MAC address. MAC address changes. It depends if you are you're on a wide area network. If you are within a local area network, your source and destination MAC address will not change. But the moment you are going from one router to another router to another router to another router, the source MAC address will change, destination MAC address will change. This I will demonstrate as we proceed in the training. But you know what? For IP address, the IP address does not change from source to destination. When you see the source IP address and destination IP address, if you grab the packet, now you guys are hearing that terminology now. You grab that packet with Wiresharks and we pieces it. We'll see where the message is coming from and we'll see where the message is going to. Unlike at layer 2, it changes from router to router at layer 2. So you need to be aware of that. You need to be aware of that. So I have tried to summarize what I have in this place. So look at what I explained to you here. IP encapsulate the transport layer segment into what? Into packets. Bring your envelope, drop it in my own envelope. That's what we call packets. And I had source IP, destination IP. And guess what? There are some devices on the road to destination. They have no business with layer 2, only layer 3. That is your router, and that is part of what is called routing. The router only needs to check layer 3 IP address to make decision. And guess what? The switch also has no business with IP address. The switch only has business with layer 2. And that is why the switch is called layer 2, a layer 2 device, and the router is called a layer 3 device. Are you seeing the connection? Router needs only the IP address to make decision. And the decision that the router is making is what we call routing. Routing is like, okay, I have the 2 routes to go to London. I can follow right, I can follow left. Which one is the best to go? Okay, I go right. That's the routing. The router does routing, the switch switches, even though the router switches also from one interface to another interface, depending on what the decision the router is making. But most importantly, most of the time, the job of a router is to route. Look at the IP address, make decision, and forward the destination. That is the job of your router. So I said the IP address does not change from source to destination, but something can change it. There's a technology called NAT, Network Address Translation. You're going to come to that. We have NAT as a topic. It's a standalone topic all by itself. And that we are going to come to much later toward the end of the training. So you need to be aware of that. So what are the characteristics of IP? How does IP behave? I like the way another person put it. He said, IP shows the road to destination. This way to London, this way to, that's the main job of IP. It does not really carry your message to the destination. The layer that does the transportation is transport layer that carries the message to the destination. IP only shows the road. So now, these are the characteristics of IP. IP is connectionless. What do they mean by that? IP is best effort. IP is media independent. Let's discuss this one briefly. IP is connectionless. IP is best effort. IP is media independent. Why did they say IP is connectionless? That's the behavior of IP. Let me give you in a simple way. If I want to call you right now, I call a line. Let's say I'm calling the class rep. Her phone starts ringing. She needs to pick the call before we can talk. When she picks the call, do you know what happens between our lines? There is a circuit that is established end to end, from my hand to our own hand, regardless of where she is in the world. That circuit is like we're the only one on that link at that point in time. And then we can begin to talk. But if she does not pick the call, there is no way I can talk to her using my phone. But you know what? I can as well write a letter and go to post office and post the letter to her, as long as I know her address. That is the way IP behaves. So when they say IP is connectionless, IP does not need an end-to-end circuit or end-to-end connection before IP will do its job. It's like post office, and that's why they give you this analogy here now. He doesn't need that. That's the way they built that protocol. So if there is a need for a traffic to be end-to-end along the line, It is another layer that will take care of that one. That is transport layer. And TCP is another protocol at transport layer, which we are going to talk about as we proceed. So IP has no business with end-to-end connection, acknowledgement, synchronization, which I was going to talk about all of this is at layer 3, layer 4, is not IP's business. The job of IP is to show the road to the destination. Transport layer carries the message to the destination. So transport layer is the one that may, mark my word now, may need end-to-end connection. It depends on the protocol that is in use at that layer. Again, we're going to come to that. So when they say IP is connectionless, it simply means it does not need end-to-end connection before it can do its job. If you just point you to the next router carries job, it points to the next router carries the job, it points to the next router, and so on. It's like post office. If I drop a letter now, I'm sending a letter to maybe somebody in Kenya, maybe Pedro. Pedro, I can't remember the country you came from. Pedro is in maybe Uganda or wherever. If I drop a letter now, one day the message will get to. That is the way IP works. But I don't forget, IP does not, okay, it's in IP, Pedro's in Ghana, okay? Don't forget, IP does not work all by itself. And that is going to still take us back to what I taught you guys at the beginning, where I talk about interaction of protocols, protocol suits. I do my part, I hand over to the next. I do my part, I hand over to the next. The next one we'll do is hand over to another one. So we're just picking IP only at layer 3, and we're talking about IP. So whether we are talking about IPv4 or you're talking about IPv6, it is connectionless. That's the way they behave. So what if it needs a connection end-to-end? Another upper layer. That is your transport layer now, takes care of that. And don't forget, they work hand in hand. They work concurrently. IP is best effort. So meaning what? Meaning what? When you have a message to send to destination, it's not the job of IP to make sure that the message gets to destination. The main job of IP is to show the road to the destination. IP wants to believe that, okay, this is your message. We are just doing our best to make sure it gets to the destination. But I will do my part. What is my part? This is the router that will take this message, that will help you to push this message to that destination. So who will now be responsible for all this transportation issue, packaging of the data, labeling the data, and so on and so forth? Transport layer has a lot to do, guys. When we come to the next layer, it has a lot to do. It has a lot of work to do. Just like they can't do it by itself also. It needs to depend on IP, because transport layer does not know the road. IP knows the road. IP shows the road. Transport layer carries the message to the destination. So when they say IP is best effort, it will just show the road and wish you best of luck that your message will get to the destination. And what if something happens along the line? Like maybe one of the packets get lost. Maybe the message didn't get to the destination the way it's supposed to be. Transport can help us to take care of that problem, because transport layer can do retransmission. You will see when we come to transport layer. It can do retransmission. It can regenerate that packet back again from the source and send to destination. But IP has no business with all of this. It has no business with acknowledgement. What is acknowledgement? I'm sending $10,000 to Pedro. Pedro will call me and tell me that he has gotten the money. That is acknowledgement. It's not the business. It's not IP's problem. Transport layer has to be the one to say, okay, Pedro, $10,000 has been sent to you. Did you get it? If you got it, then I'll get acknowledgement. Acknowledgement is like confirming that you got something. That is part of the job of transport layer, not IP. So when they say IP is best effort, it will not guarantee delivery of packet. Thank you, Mr. Sunday. It doesn't guarantee the delivery of packet. It does not have any business with acknowledgement. It doesn't even know if the next device on the road to the destination is operational. It just receives the packet and know that, okay, the next person that will help us to get to the destination is this guy on the road. Then they push it to the next person. That is the job of IP. When they said IP is media independent, thank you guys. Meaning what? IP does not care the channel you're using. It can be wired, it can be wireless, it can be fiber, it can be anything. IP works. It's not, it works on wire, it doesn't work on wireless. It works on wireless, don't know. It's not the IP-based problem. As long as it's based on our Ethernet technology, it works. It works. Regardless of the LAN technology, regardless of the wide area network technology, it works. So that is what they meant by media independent. IP, part of the characteristics of IP is media independent. It doesn't matter the media, IT works all over. It doesn't have a problem with that. Another point we need to talk about is MTU. What is MTU? Maximum transmission units. There is a maximum transmission, or let me say size of packet that can be sent over the network. I think it's 1500. 1500. Yeah, 1500. Yes, it should be 1500. So if anything happens along the line and your packet is more than 1500, what is going to happen? When I say 1500, let me explain myself. If I want to eat food right now, I cannot carry the plate of food and just pour in my mouth. I need to go section by section, spoon by spoon. And if it is swallow, I will form it based on the size of my mouth that I can take at a go, which will be different from another person. And that will be different from another person. And these are part of what protocols take care of for us, end to end. The devices that need to communicate, need to talk about, okay, you want to start pushing food across to me. What size are you going to, what size can you take at a go? And so on and so forth. But there are some configurations we can do on our router that can add to the data beyond the normal size. That is maximum transmission unit. So along the line, fragmentation can help us to take care of this kind of problem. But these are dicey things. I don't want to go into that because they are advanced concepts. These are dicey things. Fragmentation is like, okay, this size of data is way bigger than what it's supposed to be. Can we piece it again into like two? So one part will go now, another part will go later, then we assemble them when they get to destination. These are some of the ideas I need you to have on MT, but I don't want to go into MT on fragmentation. It's way beyond the CCNA level. So that is that on that part. So let me finish, then we can go for, I will soon be done, can go for questions. I've talked about EDA. When I say EDA, you should ask me which one am I talking about. So don't just hear me, EDA. Back in those days as a student, when I hear EDA, this thing was very confusing back in those days. So you should ask me for the specific EDA because it could be segment header, packet header, frame header. So, but in this scenario now, in this context now, we're talking about packet header. What is inside that packet header? I've talked about that. Source IP address, destination IP address. Every sender must put that. Because all the devices on the road to destination, they need to know where the message is coming from and where the message is going to, especially the router that needs that information. Where is the message coming from and where is the message going to? And that's why I like what they put here. The information in the header is used by all layer 3 devices. Which device is our layer 3 device? Our router. All layer 3. It doesn't matter the numbers of routers on the way to destination. They need this packet header. That's where their business is. That's their own area of interest. They want to see where it's going to. Because it is when they know where it is going to, they now know who to pass the message to. Who is the next on the road to the destination? Are we branching right? Are we branching left? Are we going straight? That's what they say a router does. Routing. All this I just explained, and that's routing. When the router is doing routing, it's moving packet from one router to another router based on the decisions it has made. And somebody has made about routing table the other time. Because the router is going to check the routing table. That's how it gets to know, okay, this guy is going to London. How many routers do we have on the road to London? Okay, this one, we can follow right, we can follow left. Which one is the fastest? Oh, then he checks the routing table. Okay, the left one seems to be the fastest, and then push the message to the left. Right? That's routing. So it checks his routing table to make that routing decision. But you cannot build that routing table without knowing the IP address of all of these destinations. You are going to see how the router builds routing table with time in this class. It doesn't know how to build. It needs the IP addresses to build. And once that table is set, then the router now can begin to make decisions. So when your message is coming, it needs that packet header and to check it and know that, oh boy, this message is going to a particular destination. So don't forget, the router used that header to make decision. And guys, this is our packets. The main packet header we have been talking about, IPv4 packet header. There are different feeds in this header. Different feeds. I'm going to only point to the most important one to us. We have the protocol feed, which point to whether you are using IPv4 or IPv6. The guys, the most important feed to us is our address feed. That is where we have source IP address, destination IP address, source IP address, destination IP address. That is the most important feed in our header, in our packet header. There are other fields we make use of. Okay, this is the protocol IP. Sorry, this is where the VB, you see. There's another thing here we call time to live. What I call time to live, the way I explain time to live to my students is funny. Time to live. If a packet is traveling from a particular source, it will have a number called TTL. TTL. And that is time to live. So if it has a TTL of, let's say, 15, that means that packet, once it crosses 15 routers, it is discarded. The packet is dead. Why? You will find out later, because of routing loop. Another way, a good analogy of this TTL is birthday. If God has given you 90 years to spend on earth, every year people greet you happy birthday, congratulations, you know that your TTL has dropped by 1. We are rejoicing with you, but your TTL is dropping. That is what happens with packets on the network. So this time to live feed, it's about how long the packet can travel from source to destination. And the source router sets that. So TTL, that is what you see. So when we capture packets header, these are the fields you see in the header. And the one we need now is the protocol feed, the version feed, the address feed, and time to live feed. Those are the ones I'm going to talk about. There are others like this total length now. If you're going to show the total length of the packet, there are others that will show so many other information, but the most important one to us are this address feed and the protocol and the version feed. Take note of that, guys. What about this one is IPv4, sorry, I should have mentioned that. What about IPv6? That's the future. That is the one we have right now. We are moving to IPv6, and now we have a lot of we have a chapter dedicated to IPv6. So I'm not going to waste time on IPv6. But the reason why we move from IPv4 to IPv6 is because IPv4 is finishing. So there's a need to move to another version of IP that will take the word to the destination. When I mean to the destination, it will be here with us for as long as possible. So we now have IP version 6, which is 128 bits. It's not like IP version 4. We've not done all of these things. We're going to do that. So you're going to see a lot more about IP version 6. So we're not going to waste time on IPv6 here. We're going to see a lot more on IP version 4. We see a lot more on IP version 6. So what if you capture the packet of IP version 6? How does it look like? Look at how IP version 6 packet header looks like. We still have the source IP address, destination IP address. This is our address feed. We have the version. You see that it's a little bit different from the IPv4 packet header because they modified the IP version 4 when they came up with IP version 6. There was some limitation, or let me say security issue in IP version 4. They solved those problems and then they gave us IP version 6. Right now, some countries are beginning to migrate to IP version 6 gradually. I heard that China has completely moved to IPv6. That I have not been able to confirm. But then the future, we also are going to have to move to IP version 6. That is why when I start teaching you guys IP addressing, I will teach you guys binary. That is conversion. We're going to do some mathematics. For those that don't like calculation, You need to prepare your mind for that class. It's not difficult, but once some people hear calculation, they just shut down. We're going to do that calculation, binary to decimal to hexadecimal. Then from there, we now go to IPv4 addressing. Then we now go to subnetting. Then I will now take IPv6. These are the topics I used to teach together before we go to router and switch configuration. So this is the most important thing in CCNA1, guys. When I say the most important, most of the things that I've been teaching you guys, anybody can read these things on their own now. But when it comes to IP addressing, oh my goodness, people have issues with this. So they need a trainer. They need somebody to teach them. IPv6, they need somebody to teach them. And most of these things I've been teaching, OSI model, TCP IP model, network devices, all of those stuff. Anybody can read all of these things if you're really serious about these things. So we're going to come into the depth of that. So if I skip some things now, it's because we still have a chapter dedicated to IPv6. We have a chapter dedicated to binary conversion. We have a chapter dedicated to IPv6. Sorry, I can see your tortoise. That's good. It's for my hand. It's raining here heavily now. Sorry, guys. Let me see. Can you hear me now? I should switch to another network. Can you give me thumbs up if you can hear me? Okay, you can hear me now. Okay, we'll soon be done. Hello, I can see the tortoise. Thank you, guys. Sorry, it's the network from here. Okay, can you hear me now? I'll soon be done. Let me just quickly finish this. Okay, so that we can give room for question. Yeah, very soon you will not hear me complain about network or just been equal. Okay, I think I was saying, so we have a chapter, that's it now. We have a chapter dedicated to IPv6, and we have